Now we're going to be looking at atomic structure, and there are certain models that you should be familiar with. Dalton's model, he sees the atom as being solid. J.J. Thomson comes along, he finds the first subatomic particle, which is the electron. After J.J. Thomson, a little bit later, Ernest Rutherford, looking at the plum pudding model of J.J. Thomson, comes along and discovers the nucleus. He has that classic gold foil experiment where he finds that the positive charge of the atom is concentrated in a small structure in the center of the atom, and most of the atom is empty space. Rutherford had a problem. He knew that there's electrons and a positively charged nucleus. Well, opposite charges attract. So why don't those electrons come crashing into the nucleus and the atom implodes? Niels Bohr gives him an answer. Bohr's model of the atom is not the most current model, but it helps to explain a lot of the things we'll be seeing in the next couple of chapters. So we want to investigate it thoroughly. We're going to start with just learning a lot of vocabulary, have a few ideas in our head, so that when you come to class, you'll be ready to learn the lesson of the day. Here's where we're going to start. We're going to start with the concept of quantum numbers. Quantum numbers is a set of 4 numbers used to describe the energy and the position of an electron. I'm going to talk about each of the 4 quantum numbers. The first quantum number is called the principal quantum number. It is given by the symbol n, a small n, and it's going to tell you the energy level or the distance from the nucleus, or the energy. This is our energy levels. The energy level is going to tell us how far an electron is from the nucleus. It's going to tell us a position, and it's going to tell us something about the energy. I have a diagram here that I'm going to swing over. This is not the entire atom, but this is going to be my nucleus, a small round structure, in the center of the atom. There's a lot of space there, and Bohr says that somewhere out there is going to come our first energy level. Now this is going to be all around the nucleus in 3D. But since I'm on the board, I'm not even going to draw a complete circle. I don't want to go that big, just a little line here to represent a certain distance from the nucleus. And here, n is equal to 1. This is our first energy level. The first energy level is here. If you look at successive energy levels, then you're going to have the second energy level, and then you're going to have the third energy level. Now I'm drawing this relative to one another because it's important to understand that as you move farther away from the nucleus, the distance between these energy levels is going to decrease. There's a lot more distance between the first and the second energy level, between the second and the third, even less distance between the third and the fourth. We're going to focus on the first 3 energy levels right now. So that's our first energy level, this is our second energy level, here is our third energy level. So n can equal 1, 2, or 3. Now, not only will it tell us the position, how far away it is from the nucleus by this principal quantum number, it also gives us some ideas to energy. Quick illustration, use it as you want. These electrons must exist on an energy level. They are not allowed, according to Bohr, to exist here, or here, or here. So the electrons must be on an energy level. They cannot exist in this space region. These electrons are negatively charged, and they have to be pulling away from the nucleus. Opposite charges attract. So doesn't it make sense that this electron doesn't have a lot of energy? It can only pull so far away from the positive charge of the nucleus before it can go no further. So if you are an electron in the first energy level, this is going to be low energy. The closer you are to the nucleus, the less energy those electrons have associated with them. Those electrons with more energy have a greater ability to pull farther and farther away. And so the farther away from the nucleus you are, those electrons are going to have higher energy. So the principal quantum number is not only going to tell me a location, it's going to tell me something about energy. Electrons found in the first energy level are going to be closer to the nucleus and have less energy than an electron found in the third energy level, where that electron is farther away from the nucleus and has more energy associated with it. Let's move on to the second quantum number. And the second quantum number is going to be lots of names. I normally refer to it as the orbital quantum number. Your textbook is going to say the angular momentum quantum number. When I learned chemistry, it was called the azimuthal quantum number. Hey, different names, but the symbol has always been, or has consistently been, a small l. This is going to tell us something about the sublevel and the shape of our orbitals. Now, N is 1, 2, 3, 4. Those are the energy levels. But N equals L. Let me draw that for you. If N equals L, then in the first energy level, we are only going to have one sublevel, and it's already drawn here. In the second energy level, there will be two sublevels. I've only drawn one. I need to put in another sublevel. So there are two sublevels in the second energy level. In the third sublevel, N equals 3. Guess how many sublevels I have to show? 3 sublevels. And so there will be 3 sublevels here in the third energy level. All right? Now, these sublevels are all designated differently. The first sublevel in any energy level is called the S. So this is an S sublevel. The first one in the second is called an S. The first one in the third is called an S. Why S? Well, these designations, letter designations, are historically developed. And you do not need to understand for this class what the significance of them are. Okay, so we have the S sublevel. Now, S's, it's going to tell us the sublevel, which gives us some information about position. S's are going to be closer than the other sublevels. They'll be closer to the nucleus than other sublevels. But it's not only going to tell us position, help with positioning, it's going to tell us something about shape. S sublevels are spherical. So what I've drawn here might be the nucleus in the center. The closest would be a 1s sublevel. It would occur at a certain distance, a certain radius from the nucleus. And then we would have the 2s sublevel, which would be found at a greater distance from the nucleus. S's are spherical, and let's remember that what I'm drawing on the board is not a sphere, it's a circle. But I can't draw in 3D. Remember that a sphere then is going to be at a certain distance from the nucleus in all directions. Okay? After we have the S sublevel, the next sublevel is called the P. The P sublevel is described as being either dumbbell or figure 8 shaped. Dumbbell or figure 8. When you're looking at a set of axes, in three-dimensional space, you would describe your x, your y, and your z plane. These p sublevels, electrons, occupy certain regions in space. And so, if we have p in the x, p in the x is dumbbell or figure 8 shape. It would look like this. And if I were to draw it on the set of axes, like this. They should be lobes of equal size and distribution. Can't draw so well today. So that's my p in the x. Then we could have p in the y. P in the y would be along the y-axis, and we would have two lobes here. And then, of course, you would see it's along the y-axis, and you can see pictures of these in your textbook in Chapter 7. And then we would have p in the z, which would be the same thing along our z-axis, and that would be occupying here and behind the plane of the board. So, if you think about this, this is a good way of maximizing your use of space. If you have a nucleus here in the center of the atom, first electrons come in and they're going to occupy this region. If another negatively charged particle comes in, it doesn't want to be in the same space. So it might occupy the Y region. And for a third electron coming in, it too would want to maximize separation distance of like charges. It might be in the Z plane. If you put this all together, if you tried this with some balloons, you'd see that the total volume of the atom is more equally distributed as far as the location of the electrons that are there. They're not bunching up in one region of space. So, we have P, dumbbell-shaped figure 8s. And after that, I'm just going to mention, we'll see these in class, that next would come the D. The Ds are going to be complex in their structure. And after that are the F sublevels, and the Fs are even more complicated. So, let's move back to this drawing. And what we see is that we have, after the S sublevel, we're going to have our P sublevels. So there is a 2P. There is also a 3P. All right? The second one's going to be a P sublevel block. And then the third sublevel in an energy level is going to be your Ds. So, in the first energy level, one sublevel, an S. In the second energy level, two sublevels, an S and a P. In the third energy level, three sublevels, an S, a P, and a D. How many sublevels would you find in the fourth energy level? Oh yeah, and you should know what the letter designations are. Okay, again, you also have some information about energy because in the second energy level, electrons found in the 2s, closer to the nucleus, are going to have less energy than electrons found in the 2p. Keep in mind, we're looking at location and energy. And then the last two things that we want to talk about quickly is called the magnetic quantum number, given by the symbol M with a subscript of L. And for the magnetic quantum number, all I'm going to have you draw right now, so we'll be ready to talk about it, is this pattern. 1, 3, 5, and 7. These are going to be our S's, our P's, our D's, and our F's. Already you can see from this that if you are drawing a sphere, there can only be one sphere with a certain radius. P's, P in the X, Y, and Z, there will be 3 positions. D's are going to have 5 positions, and F's will have 7. So, using those odd numbers, we have S with 1, P with 3, D with 5, F with 7. We could even put P in the X, P in the Y, P in the Z. And to finish, we'll end with the spin quantum number, given by the symbol ms. And we'll be talking about that in class. It's all very complicated. We need to do it face to face. So get this in your notes. We'll proceed from here.